Hey there! Welcome to this quick guide on mastering trigonometric identities. Think of this as our chat over coffee, where we break down what might seem like a complex topic into simple, manageable pieces. Today, our main goal is to get really comfortable with the fundamental building blocks of trigonometry. By the end of this video, you'll be able to confidently work with the Pythagorean reciprocal and quotient identities to solve problems. Specifically, you will learn to use reciprocal identities to find relationships between trigonometric functions, use quotient identities to rewrite tangent and cotangent, and use Pythagorean identities to solve for missing trigonometric values. Ready to dive in? Let's start with the first set of identities. Our first topic is reciprocal identities. These are essentially definitions that show how the 6 main trigonometric functions are related through their reciprocals. Let's list them out. Cosecant, written as CSC theta, is the reciprocal of sine theta. So CSC theta equals 1 over sin theta. Likewise, secant theta, or sec theta, is the reciprocal of cosine theta. We can write that as SEC theta equals 1 over cos theta. And finally, cotangent theta, or cot theta, is the reciprocal of tangent theta. So cot theta equals 1 over tan theta. These 6 equations show us that if we know the value of sine, cosine, or tangent, we can automatically find the value of its reciprocal, and vice versa. They are 2 sides of the same coin, so to speak. Now, let's work through a couple of examples to see this in action. For our first example, let's say we're given that sine theta equals 3 over 5. Our goal is to find the value of cosecant theta. Using our reciprocal identity, we know that cosecant is the reciprocal of sine. So CSC theta equals 1 over sin theta. Now we just substitute the given value for sine theta. This gives us 1 divided by 3 over 5. Remember, dividing by a fraction is the same as multiplying by its reciprocal. So CSC theta equals 5 over 3. See, it's just flipping the fraction. Let's try another example, but this time with secant. Suppose we are given that cosine theta equals the square root of 2 over 2, and we need to find secant theta. We recall that secant is the reciprocal of cosine. So our identity is sec theta equals 1 over cos theta. Plugging in the value for cosine, we get 1 over square root of 2 over 2. This simplifies to 2 over the square root of 2. In mathematics, we prefer not to have a square root in the denominator, so we'll rationalize it. This just means multiplying the numerator and denominator by the square root of 2. When we do that, we get 2 times the square root of 2 in the numerator, and the square root of 2 times itself, which is 2 in the denominator. The 2's cancel out, leaving us with just the square root of 2. For our third example, let's work backwards. Let's say we are given that cotangent theta is 4, and we want to find tangent theta. Here we use the identity cot theta equals 1 over tan theta. We can rearrange this to say tan theta equals 1 over cot theta. So tan theta equals 1 divided by cot theta. Plugging in the value for cotangent, we get 1 over 4. And there you have it. Tangent theta is 1/4. Reciprocal identities are essentially just fractions and their flips. They're a powerful tool for connecting the different trig functions. Next up, we have quotient identities. These 2 identities are incredibly useful because they show how tangent and cotangent can be expressed in terms of sine and cosine. The first one is tangent theta equals sine theta divided by cosine theta. The second is cotangent theta equals cosine theta divided by sine theta. Notice how the second identity, for cotangent, is just the reciprocal of the first one, for tangent. This makes perfect sense, right? Because we already learned that tangent and cotangent are reciprocals of each other. So if tangent is sine over cosine, then cotangent must be cosine over sine. It all connects. Let's apply this with a couple of examples. Suppose we are given that sine theta is 12 over 13 and cosine theta is 5 over 13, and we need to find tangent theta. We'll use our quotient identity for tangent. We write tan theta equals sin theta divided by cos theta. Now let's substitute the given values. We have 12 over 13, all divided by 5 over 13. Notice the common denominator? We can cancel them out directly. This leaves us with 12 over 5. So, tan theta equals 12/5. Let's work through another example. This time, we'll find cotangent. Let's say sine theta is 1 over the square root of 10, and cosine theta is 3 over the square root of 10. We need to find cotangent theta. This time, we'll use the quotient identity for cotangent. Cot theta equals cos theta divided by sin theta. Substitute the values. We have 3 over the square root of 10, all divided by 1 over the square root of 10. Again, the denominators cancel out, and we're left with 3 over 1, which is simply 3. So, cot theta equals 3. Okay, one more example. What if we only know tangent and not sine and cosine directly? Imagine we are given that tangent theta is 0.75, or 3/4, and sine of theta is positive. We need to find cosine theta. Let's start with our identity tan theta equals sin theta over cos theta. We need to solve for cosine, so let's rearrange this equation. We can multiply both sides by cos theta and then divide by tan theta. So we have cosine equals sine over tangent. Let's substitute in the tangent value, which is 3 over 4. This means cosine theta is equal to sine theta divided by 3 over 4. This is the same as sine theta times 4 over 3. So cosine theta is 4/3 of sine theta. This might look a bit different. The point here is to show that these identities can be used to set up relationships. Knowing that both tangent and sine are positive tells us that cosine must also be positive. Quotient identities help you see these connections. We've reached our final and arguably most important identity, the Pythagorean identity. This identity comes directly from the Pythagorean theorem. A squared plus b squared equals c squared, applied to a right-angled triangle in the unit circle. The identity states that sine squared theta plus cosine squared theta equals 1. No matter what the angle theta is, this relationship always holds true. This is a fundamental law of trigonometry. Now it's really important to read this correctly. The squared part, the little 2, means you take the value of sine theta and then square the whole thing. It does not mean sine of theta squared. In other words, sin squared theta is a shorthand for sin theta squared. Keep that in mind to avoid common mistakes. This main identity can be rearranged into 2 other useful forms by simply dividing by sin squared theta or cos squared theta. Let's see them. First, if we divide everything by sin squared theta, we get 1 plus cotangent squared theta equals cosecant squared theta. Second, if we divide everything by cos squared theta, we get 1 plus tangent squared theta equals secant squared theta. These are also part of the Pythagorean family of identities. Now let's see how powerful these are with an example. Let's say we're told that sine of theta is 4 over 5 and the angle is in quadrant 2. We want to find the value of cosine theta. This problem would be very difficult if we didn't have identities. But with the Pythagorean identity, it's a breeze. Let's use our main identity. We know sin squared plus cos squared equals 1. We can rearrange it to solve for cosine squared. Cos squared theta equals 1 minus sin squared theta. Now we substitute the value of sine. So cos squared theta is 1 minus the square of 4 over 5, which is 1 minus 16 over 25. Finding a common denominator, we get 9 over 25. To find cosine, we take the square root of both sides. This gives us cos theta equals plus or minus 3 over 5. Which sign do we use? This is where the information about the quadrant comes in. We're told the angle is in quadrant 2. Remember that in quadrant 2, cosine values are always negative. Therefore, our answer is negative 3 over 5. Cos theta equals negative 3 over 5. Let's work through a second example using a different Pythagorean identity. Suppose we are given that tangent theta is 2 and the angle is acute. We want to find secant theta. Since we have tangent and want secant, the identity 1 plus tan squared theta equals secant squared theta is perfect for us. 1 plus tanth il sectus. Let's substitute our value for tangent. We get 1 plus 2 squared equals secant squared theta. 2 squared is 4, so 1 plus 4 is 5. Secant squared theta is 5. Now we solve for secant by taking the square root. Secant theta is plus or minus the square root of 5. Again, we need the quadrant information. We're told the angle is acute. An acute angle is in quadrant 1, where all trigonometric functions are positive. So, our answer is the positive square root of 5, sec theol 5. Our third example on the Pythagorean identity will focus on proving that something is true. We are going to prove a new identity. The identity we want to prove is that tangent squared theta minus sine squared theta is equal to tangent squared theta times sine squared theta. When you're asked to prove an identity, the best strategy is to start with one side and manipulate it using the identities we've learned until it looks exactly like the other side. Let's start with the left-hand side, which looks a bit more complicated. We will work with the expression tangent squared theta minus sine squared theta. A great first step in any trig proof is to convert everything into sines and cosines. We know that tangent theta equals sine theta over cosine theta. So tangent squared theta becomes sine squared theta over cosine squared theta. Now we have a subtraction of fractions. To subtract, we need a common denominator, which is cosine squared theta. Let's rewrite the second term. We can write sin squared as sin squared over 1, and multiply the numerator and denominator by cos squared to get sin squared cos squared over cos squared. Now that we have a common denominator, we can combine the numerators. This gives us sine squared theta minus sine squared theta times cosine squared theta all over cosine squared theta. Take a look at the numerator. Do you see anything we can factor out? Yes, both terms have sin squared theta. Factoring out sine squared theta leaves us with 1 minus cosine squared theta inside the parentheses. Does the term 1 minus cos squared theta look familiar? It should. It's one of our rearranged Pythagorean identities. We know that sin squared plus cos squared equals 1, which rearranges to 1 minus cos squared theta equals sin squared theta. Let's substitute that back into our expression. Our left-hand side now becomes sine squared theta times sine squared theta all over cosine squared theta. This is sine to the 4th over cosine squared. This still doesn't look like our target. Let's go back a step. Instead of sine to the 4th, let's keep it as sin squared times sin squared. This gives us sin squared theta over cos squared theta, multiplied by sin squared theta. LH equals sin squared theta over cos squared theta times sin squared theta. And what is sine squared over cosine squared? That's right, it's tangent squared. So we have tangent squared theta times sine squared theta. Look, that's exactly our right-hand side. We have proven the identity. Amazing! Let's quickly recap what we've covered today. We started with reciprocal identities, which tell us how functions like secant and cosecant are the flips of sine and cosine. We learned that cc theta is 1 over sin theta, sec theta is 1 over cos theta, and cot theta is 1 over tan theta. Then we moved to quotient identities, which show the relationship between tangent, cotangent, sine, and cosine. We saw that tan theta equals sine over cosine, and cot theta equals cosine over sine. And finally, the most powerful of them all, the Pythagorean identities. The cornerstone is sin squared plus cos squared equals 1, and its two variations, 1 plus cot squared equals csc squared, and 1 plus tan squared equals sec squared. These identities are the building blocks for all of trigonometry. Mastering them opens the door to simplifying expressions, solving equations, and proving more complex identities. Now it's your turn to practice. Remember, the only way to get good at this is by doing it. So here are a few practice questions for you. Pause the video here and try these yourself. Trust the process. If you get stuck, rewind and rewatch the examples for a refresher. Don't look at the solutions until you've given each one a serious try. Good luck. Okay, welcome back. I hope you gave those practice questions your best shot. Now, let's go over them together. First up, we had to find cosecant theta, given that cosine theta is -1/2 and the angle is in quadrant 3. To find cosecant, we first need to find sine. The Pythagorean identity, sin squared plus cos squared equals 1, is perfect for this. Rearranging it, sin squared equals 1 minus cos squared. Substituting our value, we get 1 minus -1/2 squared, which is 1 minus 1/4, giving us 3/4. Now, taking the square root, sin theta equals plus or minus root 3 over 2. The angle is in quadrant 3, where sine is negative, so sin theta is negative root 3 over 2. Finally, we use the reciprocal identity for cosecant. Cosecant theta is 1 over sine theta. That's 1 over negative root 3 over 2, which is negative 2 over root 3. Rationalizing the denominator, we get our final answer, negative 2 root 3 over 3. Let's look at the second question, simplifying a fraction. Hopefully, those expressions in the parentheses look familiar. They're both Pythagorean identities. The numerator, 1 plus tan squared, simplifies directly to secant squared. The denominator, 1 plus cot squared, simplifies to cosecant squared. So our fraction becomes secant squared over cosecant squared. We've simplified it, but we can do even better. Let's rewrite secant and cosecant in terms of sine and cosine using our reciprocal identities. Secant squared is 1 over cosine squared, and cosecant squared is 1 over sine squared. Our expression is now 1 over cos squared divided by 1 over sin squared. To divide fractions, we multiply by the reciprocal of the second one. This gives us sine squared over cosine squared. And we know that sine squared over cosine squared is just tangent squared theta, a nice, clean simplification. And for our final practice problem, we have another proof. We'll again start with the left-hand side, as it looks like we can do some work there. LHS equals sin t by t equal y less t2. This is a binomial squared. We need to FOIL it out carefully. It's the first term squared, sine squared theta, plus 2 times the product of the two terms, which is 2 sine theta cosine theta, plus the second term squared, cosine squared theta. Combining the middle terms, we get sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. Take a moment to look at this expression. Do you see anything familiar? Of course. The Pythagorean identity is right there. We have sin squared plus cos squared. We know this simplifies to 1. Let's substitute that into our equation. The left-hand side simplifies beautifully to 1 plus 2 sine theta cosine theta. And that, my friend, is exactly the right-hand side of the identity we were asked to prove. Success. And that's a wrap. We've made it through the core trigonometric identities. We started with the goal of understanding reciprocal, quotient, and Pythagorean identities. Through our chat and the worked examples, we've now seen how each of these is a vital tool in the trig toolkit. You now know the basic relationships between all 6 trig functions and have seen how to use them to find missing values, simplify expressions, and prove other identities. This is a massive first step, so give yourself a pat on the back. My final piece of advice? Practice, practice, practice. The more you work with these, the more intuitive they'll become. Thanks for joining me, and keep exploring the wonderful world of mathematics.